So, good evening to everyone who have joined us live today for the discussion of Class 12th NCERT Exercise Solution Series of Physics. Today we are taking up Chapter 6, which is your Electromagnetic Induction EMI. And as you guys know, that NCERT forms the basis for your Class 12th board exam preparation as well as for your NEET UG preparation. So today we'll be taking up all the questions that are given in the NCERT exercises, dissect them out and understand the concepts associated with each question and discuss each answer in detail. So before starting with the session, a brief introduction about myself. I'm Sashwat Mishra, currently a third year MBA student at AIMS Raipur. Previous to this, I was at IIT-K where I was in engineering physics branch and I secured 9.8% CGPA in the first year before dropping out to pursue MBBS from AIMS Raipur. So that's enough introduction about me. Before starting forward with the session, I would like to implore two things. The first is if you guys get inspired and motivated after watching these live free YouTube sessions and want to take personalized one-to-one classes from us with dedicated mentorship as well as doubt solving and regular tests and assessments for being in a good place in your NEET and JEE preparation. You can contact us at the contact number given below in the description box of this video. Uh, as well as while solving the questions, if anyone has any doubts in any part of the question, then please feel free to bring it down in the comment section in the YouTube. After solving all the questions, I'll have a glance over the comment section, and if anyone has any doubt, then I'll try to clarify them before ending the session. So today moving forward, we'll have 8 questions. And yeah, so without much further delay, let's get on and start with this session. So here is the first question right in front of us. Let's read the question statement first. Predict the direction of the induced current in the situations described by the following figures A to F. So we have 6 situations, 1, 2, 3, 4, 5, and 6. And we have to predict the direction of the induced current, or in other words, the direction of the induced EMF in each of the following cases. So before starting with the answer, let's discuss what is the concept of the uh, formula which is to be used here. And I guess many of you have know what is to be used here. It is the very famous Lenz's law. Okay. Now, what does Lenz's law say? That the direction of the induced EMF can be depicted as minus d phi upon dt, where this d phi upon dt is the rate of change of the flux, the rate of change of flux, and this negative sign indicates that the induced EMF always, always opposes the cause that produced it. Always opposes the cause that produced it. That means if I have a coil of wire over here, okay, and I try to bring in a magnet, okay, with the north pole in it, okay, towards it, then the current induced in this coil would be such that this will try to repel this magnet. In other words, this face of the coil, this face of the coil which is facing the magnet will also start behaving as the north pole. In that way, like poles will repel each other, right? So again, we need to know in what direction, if the current flows, it acts as the north pole. Okay. So while seeing at the coil right in front of us, uh, if in the coil the current runs in the anti-clockwise direction, in the anti-clockwise direction, okay, then considered, that is considered as the north pole. Okay. And while seeing at the coil, if the current moves clockwise, if the current moves clockwise, then it is considered as the south. Okay. So these two figures you need to remember. How anti-clockwise means north pole and clockwise means south pole. Okay. So this is Lenz's law. This negative sign is the Lenz's law. Now let's apply this law to each of the six cases over here. Okay. So in the first case, we have a coil of wire. Okay. And we are bringing in the south pole here. Okay. While bringing the south pole to the face of the coil, the current should be such that this side, which I'm highlighting now, this should behave as the south pole. And what is south pole? It's the clockwise motion, right? So here the current will be set up in a clockwise fashion, right? If we view it from this side, if we view it from this side, then the current should appear to us as clockwise, right? So if it is clockwise, then this current will go like this, okay, and return over here, okay. So the direction of the current or the induced current would be Q R P Q. Will go like this in the loop, okay. So this is the direction of the current which is induced in the first case. Now, in the second case, we have two coils, okay? So let's first consider the first coil. Here, the south pole is being brought to the coil, this left side coil. So this face, which is facing the south pole, should behave as the south pole. In other words, or it should repel this south pole, right? So in other words, this face should have a current which is clockwise sense, okay? So while if we look from this side, they should appear as if it's a clockwise current, right? Like this. So the current would be like this. The current would be like this. So in the circuit, we should have a current like this. Okay. So in this sense, the current would be PRQ. Okay. The sense of the current would be from PRQ. Now, in this case, in this case, the north pole is actually moving away. If the north pole is actually moving away, then what should happen? Legislators said that it should always oppose the cause. That means if the north pole is moving away, this should act in such a way that it will bring it towards, because the cause was moving away, so it should bring it towards the coil. In other sense, this should act as the south pole, okay? Or in other words, if we see from your this side, if we see from this side, this should be acting like a south pole or in a clockwise fashion. Okay. So the current should be like this for us if we view it from this direction. Okay. Just need a bit of imagination over here. Okay. So if we view from this side, the current should be like this. So in the circuit, the current should be like this, right? The current should be like this, or it should be in the YZX sense. Okay, so I guess this case is clear to everyone. Then moving over to the next case. In this case, we have a tapping key in this circuit which is just closed, and due to that, the current is flowing in this clockwise sense when viewed from this side. Okay, and as it is just closed, there will be a change in the flux, okay, from zero to some value, and that change will induce a current in this circuit. Okay, now from this side looking, it looks like a clockwise sense, right? Current is moving in a clockwise sense, so this should act like a south pole. Okay, now if this acts as a south pole, then to oppose this, this should also act like a south pole. Now, how will it act like a south pole? If viewed from this side, this coil should be in a uh, clockwise sense. Okay. So how will it be? Current should flow like this. Okay. So if the current flows like this, then uh, it will appear as if moving clockwise in from this side, and hence it will oppose the cause. So the sense of the current in this case is again Y, Z, X, Y. Okay, so I hope this is clear to everyone. Next, moving on to the fourth case over here. In the fourth case, we have the circuit like this, okay, and rheostat setting is getting changed. That means the current is getting changed, okay, current is changing, and due to the current changing, there is a changing magnetic field also. So that is the source of the EMF, okay. And viewed from this side, if I view from this side, okay, the sense of the current is actually like this, which is anti-clockwise, right? So it should act like a north pole. So if this is north pole, then this should also act like a north pole, okay, to oppose this. And that is, if I view from this side, it should be a north pole or in the anti-clockwise direction. And so the current should flow like this, okay? So again, the sense of the current will be, uh, no, from this side, if I see, it should be a clockwise sense, okay? So for clockwise, uh, anti-clockwise sense, so it should be like this. So the sense of the current again would be Z, Y, X, Z. Okay, so I guess this is clear to everyone. So moving over to the fifth case. Okay, in the fifth case, here the tapping key is just released. Okay, so this is a break current, right? When the current is suddenly stopped. So if the current is suddenly stopped, the current initially was moving like this. Okay, current was moving like this. Okay. So this was, you know, acting if viewed from this side, it was again an anti-clockwise. Okay. So this was acting like a North Pole. Okay. This was acting like a North Pole. Uh, okay. So till this point, it's clear. Okay. So if it was acting like North Pole, okay. So on this side, in the second circuit, okay, this North Pole, this when the key is just released, okay, just released means it's a break current, okay. And if the current is broken from this, if it goes to no current, then it will act like a South Pole, okay, because it's a break current. If it had been a make current, it would be like a North Pole. If it's a break current, it will be opposite like a South Pole, okay. And so this should also act like a South Pole when viewed from this side. And for viewing from this side, if it acts like a South Pole, it should be along the clockwise sense, okay. So this should be the sense of the current, okay. So if this is the sense of the current, it should go like this or X, R, Y. This should be the sense of the current, okay. X, R, Y. Now, moving on to the last case. Here, the current I is decreasing at a steady rate, okay. So the magnetic field due to the current, which is mu naught I upon 2 pi r, okay, at any distance r. Okay, this is the magnitude of the magnetic field. But if you see, if this is a current carrying wire, then from the right hand rule, okay, from the right hand rule, the magnetic field is actually in the plane of the ring only. Okay, the magnetic field is actually in the plane of the ring. So there is no flux. Okay, because what should the flux, which is B dot A, right? Should B dot A. So it is BA cos theta. This is B, the plane of B. This is the plane of A. Among that, there is 90 degrees angle. So this should tend to 0, cos 90 0. Okay, so no flux. There is no flux which is passing through the plane of the loop. Hence, in this case, there is no induced current. Okay, there is no induced current in the loop. So I hope this clears all the six cases. First, we understood what is the Lenz's law, and we saw that north is anti-clockwise sense and south is clockwise sense. And using that, we discussed each of the six cases. So I guess this question is pretty clear to everyone. Okay, so let's move on to the next question. Before that, let's check the YouTube section if anyone has any doubts. Each of the six cases. So, okay, so no one has any doubt in any part. So moving on to the next case. Okay, the next case is something like this. Okay, So, yeah. So let's move on to the second case over here, which says use Lenz's law to determine the direction of the induced current in the situations described by figure this. Okay. In the first case, we are having a wire of some irregular shape, which is given to us, okay, which is turning into a circular shape, okay. So this is turning, okay. So this wire is turning into a circular shape, okay. From the irregular shape, it's turning into a circular shape, okay. This dotted line is representing the circular shape into which it is turning, okay. So in this case, uh, when the shape of the wire changes, the flux through the, see, in this case, this was the area which was exposed to the magnetic field, okay? But when it completely became circular like this, of course, this much amount of area is increased, which is being exposed to the magnetic field, okay? So this much amount of area is increased, okay? So, so what happens is the flux increases, okay? So this d phi upon dt increases, okay? As a result, the induced current will, as per Lenz's law, it will induce an opposing current, okay? So that opposing current should should oppose the magnetic field, okay? Should oppose the magnetic field. The magnetic field is along into the paper, okay? So the induced current should be in such a way in the circular loop that the magnetic field will come outside the induced current, okay? So how is that possible if the current is moving anti-clockwise, okay? So otherwise, the sense of the current in this case would be along ADCP. ADCP, okay? ADCP. All right, so this is the answer to this question. So A bit is done. In the second bit, we are saying a circular loop is being deformed into a narrow straight wire. Okay, this was a circular loop earlier, but now it is being deformed like this, okay, into a narrow straight wire. And in this case, what should happen? This much amount of area, okay, this much amount of area of exposure to the magnetic field is actually decreasing in this case, okay. This much is increasing, but as you can see visually only that the total net area exposed is being decreased, okay. So this d phi upon dt is decreasing and the current induced, okay, the current induced should be such that it should support the magnetic field in this case. The current induced should support the magnetic field, support the magnetic field in this case, okay, because the d phi upon d phi dt is decreasing, okay, and here the magnetic field is actually coming out of the plane of paper. So the current should be such that it should support. That's it. That means the induced current should also be like coming out of the plane of paper. Okay. So again, when is that possible? Uh, when the current is again in a anti-clockwise fashion, right? So if the current is in the anti-clockwise fashion, again it is ADCBA. Okay, again this is ADCBA direction. Okay, so always remember that induced EMF always opposes. Okay, so that means if it's decreasing, the d phi upon dt is decreasing, then it will support the magnetic field. Okay, opposes doesn't mean that always it will oppose the magnetic field. It opposes the rate of change of this flux. Okay, doesn't oppose the magnetic field. It opposes the rate of change of the magnetic flux. Okay, so I hope this question is also clear to everyone. Then let's move on to our next question. Okay, so this is our next question over here. Okay, so let's read out the question first. The question says, we have a long solenoid with 15 turns per centimeters. Okay, and has a small loop of 2 centimeter square area placed inside the solenoid normal to its axis. Okay. If the current carried by the solenoid changes from 2 amperes to 4 amperes in zero point 0.1 seconds steadily, what is the induced EMF in the loop while the current is changing? Okay. So in this case, the number of turns, okay, of the solenoid is given as 15 per centimeter, right? So which is 1500 per meters in SI units. Okay. All right. Now the area of the loop is given as 2 centimeters squared, which is 2 into 10 raised power minus 4 meters squared in SI units. And the current carried changes from 2 amperes to 4 amperes in 0.1 seconds. Okay. So the induced EMF is d phi upon dt. Okay, the magnitude. Okay, and here this phi is the magnetic field times the area because if this is the solenoid, if I draw the figure, okay, solenoid is wrapped around this material, let's say, okay, and inside that I am having a loop. Okay, now inside a solenoid, the magnetic field is straight lines, right? So if this is the magnetic field, okay, and the area element of the loop will be like this, okay, normal to the surface. So B dot L will just be BA, okay. So we need to find the magnetic field inside this solenoid, okay, and which is your B inside a solenoid is mu naught N I, okay. So your induced EMF, which is d phi upon dt equals d upon dt times VA. Here A is the constant, which is the area, so we take it out and we do d upon dt of the magnetic field, which is mu naught N upon L, that is the number of turns over the length, upon the length, into the current, okay? So this will be A mu naught is again common, we take it out. N upon L is also common, so we get di upon dt, okay? So from this expression over here, I changes from 2 amperes to 4 ampere, zero point 0.1 seconds steadily. So your di upon dt will be 4 minus 2 upon zero point 0.1 amperes per second. So this will be 20 amperes per second, right? Okay, so now plugging in the values, we have A, which is 2 into 10 raised power minus 4 into mu naught, which is 4 pi 10 raised power minus 7. Okay, n upon L is given as 1500s. Okay, and di upon dt is 20. Okay, so if you solve this equation, the answer will be 7.5 into 10 raised power minus 6 volts. Okay, so this is the induced EMF in the small circle, the small coil which is placed inside the solenoid. Okay, so I hope everyone is clear. So you need to know this formula for the magnetic field in the solenoid. Okay, and E equals d phi upon dt. Okay, so I guess everyone is clear with this question. So moving forward with the next question. Okay, this question number 4. Let's read out the question statement first. We have a rectangular wire loop of sides 8 centimeters and 2 centimeters. Okay, with a small cut is moving out of a region of uniform magnetic field of magnitude zero point 0.3 Teslas directed normal to the loop. Okay, what is the EMF developed across the cut if the velocity of the loop is 1 centimeters per second in a direction normal to the longer side, shorter side of the loop? For how long does the induced EMF last in each case? So we have a rectangular loop, okay, and it's moving out of a region of magnetic field, okay, which is uh, perpendicular to the loop, okay, which is zero point 0.3 Teslas, and the side lengths are 8 cm and 2 centimeters, okay. And in the first case, the velocity is actually perpendicular to the longer side, which is 1 centimeters per second. And in the second case, the velocity is perpendicular to this side, which is again 1 centimeters per second. So we need to find in each case what is the induced EMF and how long does this induced EMF last. Okay. So the length is 8 centimeters, which is 0.08 meters. The breadth is 2 centimeters, which is 0.02 meters. And the area is L times B, which is 16 into 10 raised power minus 4 meters squared. Okay. And magnetic field strength is zero point 0.3 Teslas. Okay. And the velocity of the loop is 1 centimeters per second, which is 0.01 meters per second. Okay. 0.01 meters per second. Now, in the first case, in this case, okay, the induced EMF is BLV, right? Everyone knows BLV, which is uh, the magnetic field, which is 0.3 into L, which is 0.08 times B, which is 0.01. Okay, so this is equals to 2.4 into 10 raised power minus 4 volts. In this expression, this L is taken uh, that side, which is perpendicular to the velocity. Okay, that is taken as the value of L. Okay, now for how long this EMF will last? Till the time this circular loop is actually in the magnetic field. Okay, now what will be the time? It will be the distance traveled upon the speed. Okay, so if it's traveling in this sense, okay, along downwards, then the distance traveled is this length, that is the breadth, which is 2 centimeters. Okay, at the speed of 1 centimeters per second. So it will be just 2 seconds. Okay, so the EMF, induced EMF, will last for 2 seconds in the first case. Now in the second case, the induced EMF will be B. It's not L this time, it will be BV. Okay, because in the second case, the velocity is perpendicular to the breadth. Okay, so this is 0.3 into 0.02 into 0.01, or the induced EMF is 0.6 into 10 raised power minus 4 volts. Okay, and the time taken in this case, the loop will move for this much length. Okay, so the distance upon the time, what is the distance? That is L upon B. Okay, what is L? That is 8 centimeters upon 1 centimeter per second, so it will be 8 seconds. Okay, so this is the answer to this question. Okay, so I hope this is clear to everyone, this question. So let's move on to the next question. Okay, I'll just box the answers. Okay, so this is the answer. This is the answer. Then this is the answer, and there's 2 seconds. Okay? Answer. Okay, so now moving on to the next question. Okay, a 1 meter long metallic rod is rotated with an angular frequency of 400 radians per second about an axis normal to the rod passing through one of its end. Okay, so I have a rod and it's rotated about an axis passing through one end of its rod. Okay, at uh, at an angular frequency of 400 radians per second. Okay, and this is a 1 meter length rod. Okay, so this is given to us. The other end of the rod is in contact with the circular metallic ring. Okay, a constant and uniform magnetic field of 0.5 teslas parallel to the axis uh, exits everywhere. So this is the direction of the magnetic field. Okay, now calculate the EMF developed between the center and the ring. Okay, so we have been given the length of the rod is 1 meters. The angular frequency is 400 radians per second. The magnetic field strength is 0.5 teslas. Okay, 0.5 teslas. Now, one end of the rod has a linear velocity, while the other hand has a linear velocity of L times omega. Okay, so the average linear velocity would be omega L upon 2. Okay, the average linear velocity of the rod, and the EMF developed will be BLV, or the average velocity in this case, which is B is 0.5. Okay, or you can say BL. The B average is L omega upon 2. Okay, so the induced EMF will be half B omega L squared. Okay, so this is half B is 0.5, omega is 400, and L squared is, okay, so this is 100 volts. Half, this is 100. Okay, so the induced EMF is 100 volts. This is the answer to this question. Okay, this figure, if I draw this, uh, this is the axis. Okay, and this is the rod. Okay, the axis and the rod, and this is rotated with omega, which is 400 radians per second. Here I have the range. Okay, so this end the velocity is 0. At this end it will be omega L. So the average will be omega L upon 2. Okay, and the magnetic field is like this, parallel to the axis. So the induced EMF will be BLB average. Okay, so I guess everyone is clear with this question. So let's move on with the next question. Okay, so this is the sixth question for today, which says a horizontal straight wire, which is 10 meters long, extending from east to west, okay, is falling with a speed of 5 meter per second at right angles to the horizontal component of the Earth's magnetic field, which is zero point 0.3 into 10 raised per minus 4 Weber per meter squared. Okay, this is in series unit Webers. So, what is the instantaneous value of the EMF induced in this wire? Okay, so the first question, the wire's length is 10 meters, speed is 5 meters per second, with which it is falling. The magnetic field is zero point 0.3 into 10 raised power minus 4, okay, Webers per meter square. So the induced EMF is BLV. Okay, so B is zero point 0.3 into 10 raised power minus 4 into L, which is 10, into V, which is 5. Okay, so the induced EMF will be 1.5 into 10 raised power minus 3 volts. Okay, so this is the first answer. The second bit asking, what is the direction of the EMF? Now we're saying that this is the rod, let's say from east to west. Okay, this is the rod from east to west, and it's falling. Okay, and the horizontal component of the Earth's magnetic field, okay, at right angles So this east end will have higher potential. Okay? This east end will have higher potential. Okay. Now the third question says which end of the wire is at the higher electric potential. Okay. So this is the east end, which is the highest potential. Okay. Now in the second case, what is the direction? We can determine the direction of the induced current by using the Fleming's right hand rule, where the current is flowing in the direction from west to east. Okay. All right. So yeah. So this is the answer to this question. Okay. So moving on to the next question, 6.7, which says your current in a circuit falls from 5 amperes to 0 amperes in zero point 0.1 seconds. If the average of 200 volt is induced, give an estimate of the self-inductance of the circuit. Okay. So we have been said that the initial current is 5 amperes. Okay. The final current was 0 amperes in a time gap of zero point 0.1 seconds. Okay. So the change in current is I1 minus I2, which is 5 amperes. Okay. And the time taken for the change is 0.1 seconds. Okay. And the average EMF induced is given as 200 volts. Okay. Now, for the self-inductance, if I can consider it as L, which is being asked in the question, okay, the self-inductance, the EMF induced, we know, is given by the formula L di upon dt, right? L di upon dt. Okay, so you need to remember this formula L di upon dt. That implies 200 equals L 5 upon 0.1, which is L times 50. So that implies your self-inductance comes out to be 4 Henries. Okay. So this is the answer to this question. Okay. So you need to remember this formula. Okay. So I guess we are done with this question. Let's move on to the last question for today, which says, so the last question says, a pair of adjacent coils has a mutual inductance of 1.5 Henries. Okay. And if the current in one coil changes from 0 to 20 ampere in zero point 0.5 seconds, what is the change of flux linkage with the other coil. Okay. So we have been given the mutual inductance is 1.5 Henries. Okay. And in one coil, the initial current is 0 ampere, the final current is 20 amperes. Okay. So the change in current is, and within the time interval of 0.5 seconds. Okay. So the change in current is I2 minus I1, which is 20 amperes. Okay. And the induced EMF, as we know, is d phi upon dt. Okay. And the EMF is linked to the mutual inductance as mu di upon dt. Okay. So d phi upon dt is equals to mu di upon dt. Okay. So you should remember this formula now. Okay. We get d phi equals uh, mu into di. Okay. Mu into di, or that equals mu is given to us as 1.5 into di is 20. Okay. So this d phi is 30 Webers. Okay. So the change of flux linkage with the other coil, that is d phi, is 30 Webers. Okay. So this question is also done. Oh, sorry. So yeah, this is the answer to this question. Okay. So I guess with this, we are done with all the questions for today. Uh, and all the formula that have been utilized and highlighted. Okay. So yeah, I guess for today we have done with all the questions. And let me check the YouTube comment section if anyone has any doubt in any of the solution. Have been utilized and highlighted. Okay. So yeah, I guess for today we have done with all the questions. And let me check the YouTube. Yeah, so no doubt in the YouTube comment section. That's a great thing. And yeah, so before winding up with the session, I'd again urge you or implore you that if you guys are inspired by our free YouTube sessions and wish or desire to attend one-to-one live uh, lectures with personalized mentorship guidance and tests and assessments, then you can contact us with the contact number given in the description box below, wherein you will appropriate thrust to your NEET and JEE preparation and be in a very good place in your preparation strategy. Okay. So we'll meet again with a new chapter in this series. So till then, this is it. Thank you guys. Bye bye. Have a good night.